Okay, describing graphs. This is one of the hardest bits that people find about motion. Most of the mathematics is fairly straightforward. However, trying to describe a pattern is really important because that is so crucial to what we're doing. The maths is based on this. So the main thing is about gradient, and we know usually how much we find gradient with, because if we just have a quick look, if you are finding the gradient of a graph, then as I've been trying to show you, it might vary a little bit, but what you need is a nice big triangle as large as you possibly can. So if it doesn't go through the origin, a bit awkward, but if it goes through the origin, well, actually take it all the way down. Okay, that's your change in your y-axis, that's your change in your x-axis, and so your average gradient, okay, i.e. straight line from there to there, okay, that straight line will be the gradient as an average, which is change in y over change in x. Okay, so for example, for average velocity. Now, it is not always that simple. We often have curves. So what we're going to do is look at the way of describing changing motion so that you can get best marks and also nice clear answers. So we have a similar thing here, and I'm going to introduce it through a different medium just so you can see why. But the key thing is, yeah, large triangle, underline, underline, make sure you've got that. So if you're finding that, that's fine. However, as soon as we've got changing patterns like we do here, particularly something changing over time, okay, so we haven't got motion here, but we do have a rate because we have time. So what we can do is find out actual values, instantaneous values at different points. So let's just make it clear. Average value, average gradient equals dy over dx. Okay, but instantaneous value, in other words, anything at an instant, at any one instant in time, it doesn't need to be the beginning, it could be midway through a journey, whatever, then that's your dy by dx. And the only way to get that is to actually use gradient of a tangent. Okay, you cannot, not from a graph, you can by calculation and calculus when you get to it, but you can't find the gradient at a certain point. So here, for example, we have hydrogen gas being produced in some sort of chemical reaction, maybe it's a metal in acid, whatever it may be, and over time it starts to have used up all the reactants, so it starts to level off. But the key for what we're doing here is we need to think about what the gradient represents. So here it is a volume, so the gradient is a change in volume per second. Okay, so it's the rate of change in volume. So if we were to try and find that point at 2 seconds, I will take my very scientific looking multiplication ruler here, and I will link that up. Oops, excuse me. And very importantly, try and get this right. So it's not about the value at that point, we're trying to find the gradient. The best, to be honest, the only way of doing this is put your pen on the point where you're trying to take your reading, and then what we will do is change your ruler, okay, like that, until you get basically about the same size gap each side, and that is your best tangent that you're going to get. Okay, and then you can start to find values, etc, etc. So you know, choose something nice, and doesn't quite go up to 5 seconds, but you could do 4 seconds. There we go. So you take your value like that, take it down, etc, and read it across. So again, what you're doing is you're changing into an average, a nice large triangle, but you've done it for that point. A millisecond later, sorry, a 2 second mark, sorry, that should be 2 minute mark, I realised. 2 seconds is too far down here, you'll never get it. But yeah, tangent at that point, you know, a second later you'll have a different gradient, so you'll have a different tangent. So that is how you do complex stuff, but the key is that it's all about the gradient. So when you're doing descriptions, stick with gradient. Okay, for what we're going to do, the area is particularly obvious, but also with any graph you might need to find the average itself, so you might need to find the area underneath. Okay, so this, for example, might find the volume at that point. You might want to know the volume that is escaped after a certain time, etc. So that will give you summation of it. Okay, so useful. Sometimes we get curves, in which case, again, like we've mentioned in a previous topic, you do your best to try and get the value. So maybe you could turn that into kind of little triangles and squares or trapeziums or something like that. Okay, that's the best way of doing it. However, back to that later, because most of our stuff is actually, most of our work rather, is actually about nice straight line graphs. Okay, so in terms of what we got going on here, we have the ones that most people struggle a little bit with, but the technique, if you use the technique, will always get you the right answers. So, just going to give me my space, which is actually on the next page when you get it. When we're looking at those, so we're going to just describe what they're showing. So again, key point, okay, what does the gradient represent? The gradient represents the change in whatever is on this axis. Okay, so that's what your key is. You've got to look at what's on your axis. And we can talk about rate because this is time. So how much change per second. Okay, that's what we mean by rate. So in this case, because of that, because y is displacement in your description, then the gradient gives you that, which in this case, change in displacement per second is velocity. Okay, so you can talk about the velocity in these graphs by looking at what the axis is doing. Okay, and that's the crucial bit. So in this case, if you had to describe this, I would say displacement is constant. Okay. So that means that the idea of graph-wise, delta S equals 0. Okay, so it's not changing. So velocity is 0. Okay, so what we've got is we've described the y-axis and then interpreted it. Okay, so that's our two-part answer. If we go on to try that one, well, we've got a constant change in displacement. Okay, so again, we're describing what goes up the axis. Okay, so let's put that so. Velocity is constant. Okay, notice that really useful way of putting it. So if we talk about displacement or whatever's on our y-axis and our change in whatever's on our y-axis, well, how it changes gives us that next step up. So constant velocity, because I've got a constant change, constant rise in displacement, constant change in displacement. Okay, as signified, phrase goes, as signified by a nice straight line. The third one, you've obviously got a lot more complicated stuff. I should say, by the way, do calculation. So if you do that, it's 20 high divided by 10, no gap at the beginning, so it's 20 minus 0 is your change, and it's divided by 10, so 20 over 10. Excuse me, 2 meters per second. Okay, so that, notice that's an afterthought, so you've got your two key parts. So let's use those two key parts again. This one is the problem, trying to describe this. So the easiest way, link it to gradient. It's much easier. So on here, the idea of gradient is the rate of change, because it's time, it's rate, time, it's rate of change. So you can put in that the you've got a change in displacement, but it's not constant. So rate of change in displacement, okay, is, and then you can fill in the gap. So it's getting steeper, so our amount of change per second is increasing, so the rate of change is increasing. Okay, and though, so what does that mean? Well, it's this, again, velocity, missed out a letter there, excuse me, velocity. So velocity is also increasing. Okay, so you've got that kind of link, very direct, very clear. Put that in all your answers. So you're describing the graph and then what it means. So velocity is increasing, which can then be further interpreted, it's accelerating. Now you don't need to put that. Okay, if you were describing something like that, you could just say, so what does that gradient mean? That gradient changing? It's the velocity is increasing. That's a perfectly good answer. Just in the back of your mind, going, well, because velocity is changing, you can do the next step, which is acceleration. Okay, now I've got the same graphs here, okay, but I've got different axes, okay, but the descriptions are the same, so keep going with that. So again, you've got your two parts. Okay, so you've got your description of graph, and then you've got your going to your meaning. Okay, obviously the meaning is different because the graph is of a different thing. But over here, for example, we have that whole idea that thingy is still constant, whatever the thingy is, and in this case it is your axis that is constant. So velocity is constant. What does that mean? Well, it's not changing speed. If you needed to put in meaning, it's kind of a bit nonsense here. Delta V equals 0. So what does that mean? Rate of change of velocity and all that stuff tends to lead to acceleration. So acceleration equals 0. Okay, graph B. So your constant, if you prefer, rate of change or constant increase. I think it sounds a lot better because you actually can say it's going up rather than going down. Constant increase in velocity. So what does that mean? Again, you've got that constant. So your gradient is steadily increasing at the same rate, so your acceleration is constant. And again, you can do your maths, equals meters per second squared. Okay, and then for the third one, again, your rate is increasing. So rate of increase in velocity. So again, I've gone a little bit more clearer than I've got here. So perhaps better answers. So rather than just saying change in, constant increase in displacement, I would, make it as clear as you can. So constant, rate of increase in velocity is increasing or growing. Don't worry about using increasing twice. It's going up, but it's going up at a higher rate. Again, the rate is a value. Okay, so don't worry about this kind of idea numbers, but try and talk about it speeding up more quickly, and don't go down that approach. Keep it simple. That is what is changing. That is, whatever's on that y-axis. So what that means is, I should put little arrows in there. So that one is, again, basically acceleration is increasing. So if this was a car, that means that someone's pushing the accelerator more and more and more as they speed up, whereas the previous one, okay, just to compare those two graphs, the previous one, the displacement's getting bigger. That means the velocity is getting bigger, but it's getting bigger at a steady rate. So someone's getting faster, their velocity is going up, but it's going up at a steady rate. Whereas here, the velocity is going up at an increasing rate. Okay, so the acceleration is off. But again, keep going back. What is the meaning of the gradient? It's the acceleration. What is the meaning of that gradient? It's the velocity. Okay, so what is changing on the graph? Displacement. So use your ideas, use your kind of equation linked to the gradient all the time while trying to get your descriptions on graphs. Okay? Now I should say, just to mimic what we've got up above, gradient is the rate of change of y over x, where y is velocity, x is time. So what you're just simply ending up with is, I'm going to put it this way, dv by dt, forget x and y, mathematicians, they get everywhere, that is acceleration. And as I say, most of the time, at least you're going to be nice and constant. It's not going to be a curve. That's getting a bit beyond what our course in terms of mathematics. However, we do get descriptions of that, or ones that curve the other way, or curve down. Okay, so curves do happen. Gradients that are changing do happen. We just tend to stay away from the maths if we can at this stage. Right, other crucial thing is to bring this back here, and this is why these tend to be the main types of graphs that we use, but do beware, you will still get displacement graphs because they actually are really useful in many circumstances. But we tend to use VOT because VT graphs because we can take velocity readings, we can find the acceleration from the gradient, and we can also find the area underneath. And if we have time and we multiply it by velocity, what we get is displacement. So we have 3 sets of variables that we can get from velocity time graphs: displacement, velocity, and acceleration. Really useful. Okay, example down here then, just to finish off. Trying to get the description. We've got a lovely straight line graph. Should be easy. But it does link into the problem that often graphs aren't just that upper quadrant, okay, of time and velocity. We have minus velocity as well. Okay, so we need to use the idea of Cartesian coordinates. We take rightwards as positive. If it's going up and down, let's take up as positive, because then we can treat it like graph. So up, positive numbers, rightwards, positive numbers, down, negative, backwards, should we say, negative. Okay, so we'll use those same principles all the time. And we'll do that with the working out, you'll see. So, what can we do? What can we say about this graph? Well, let's give it some detail. Break it down. It's all about the velocity. So, we start off with a value. That's always crucial. Where are we starting? So, initially, velocity equals 5 meters per second. Taking this bit as well, rightwards. Okay, so that gives us a full answer. We've got a direction, we've got a speed, etc. So that's our starting place. Now, if we then say, okay, what's going on? Well, the velocity is going down. So why not just put that? Velocity decreasing. It's going down. It's going down in a straight line at a steady rate or at a constant rate, whichever. Can we add some maths? Yes, we can. So we've got a velocity, we've got a time, 5 and 5, so of minus 1 meter per second every second. Okay, so I've got a gradient there, I've got a value. Okay, so I've done a little bit of math calculations, but the crucial bit is what is here is going down, so I'm saying what it's doing, and the shape of the going down. So it's a steady rate as it decreases. Okay, it reaches 0. So I'm going to add that on there, because otherwise I'll need 5 steps to stop after 5 seconds. I'll fit it in there. Okay, so it's crawled to a halt, it's slowed down to a halt, and then it carries on at the same gradient, but my velocity is getting bigger, more and more negatively. Okay, so actually the velocity is now increasing at a steady rate. So notice I've only just swapped that around. Steady rate of -1 meters per second squared. Okay, so I've still got the same rate, I've still got the same gradient. Okay, however, what it means is that something's changed because I'm going negative still. Well, I'm still slowing down, but you can't slow down below 0, but you can get faster again. So what I've got is this negative velocity. So we end up by going back up to this idea of the gradient. So sorry, gradient onto the graph axis. Okay, so what are we doing here? So velocity increasing a steady rate, ... as it accelerates leftwards. Okay, so it's actually speeding up. You could go on and say reaching a final velocity of, or we could do it as for another 5 seconds. So you've linked in your axes anyway, because you've got a rate, you've got a time, so therefore you can find the third component, which is velocity. Likewise, we have velocity, we have time, so you could work out, it links it all together. Okay, that's why you didn't really need to say that as such, because you've already kind of linked that. But yes, we've got different things. We've got slowing down, we've got speeding up. They're both doing it at the same rate though. Okay, so it's something comes flying and stops and goes back again at the same rate as it came in. Okay, so there's a lot that you can pull out, but when it starts to get complicated, this is when you must fall back down on your crucial things. What is happening to your vertical axis, your variable that you're interested in? What does that mean? Okay, so both of those are really important. Okay, thank you very much, guys.